Let's take a little break from the world of zeros and ones for at least one lecture. I think we deserve that after the last lecture. So for this lecture, I want to talk about the Burrows-Wheeler Transform. And in the spirit of taking a break, not only are we going to be taking a break from zeros and ones, because nowhere in this lecture will I be talking about a compressed bit stream, but in fact, in a certain sense, we're going to be taking a break from achieving any compression, because this thing is a transformation. The Burrows-Wheeler, okay, actually, that's already too much of a mouthful. I'm going to call that the BWT. The BWT takes a piece of data and performs a transformation that manipulates the data and then produces this new piece of data, which is basically the same size. If I take the BWT of some sequence of data S, what comes out, the finished product, will be about the same size as what went in. It'll actually be a tiny bit bigger, but always predictable. I don't expect to achieve any compression when I apply the BWT. But the reason that I like it, the reason that it's relevant to a compression course, is that applying the BWT manipulates the data. It rearranges it in a way that allows me to amplify other compression techniques, especially relatively simple ones, which is great because after the last few lectures, I think you'll agree, more complicated compression techniques can eventually become a little bit of a headache. So in this lecture, I want to talk about how to perform the BWT. And if we're going in this direction, we take our input data and then compute the BWT. I guess we'll call that the forward direction, the forward BWT. We also have to talk in this lecture about how do I reverse it. Because if I want to employ some transformation while performing compression as part of a larger compression scheme, then of course I need to be able to take what came out of the transformation on the compression side and run it through some kind of inverse operation to recover my original data. So this lecture will be spent talking about the forward BWT and the inverse BWT, the Burrows-Wheeler Transform. So to get started, let's take a look at this piece of data. So this sequence, like many of the sequences we've worked with so far in this course, is pretty short and pretty straightforward, pretty simple. It only has a limited set of symbols. These are the symbols from the home row of the keyboard. And it does actually have a few patterns that we might identify. If we're searching for patterns the way we would when we were talking about LZ schemes, we would probably zero in on 3-character or larger patterns. But unfortunately, I don't see any patterns larger than 3 characters that reappear, so I do see these. These are 3-character patterns, space SA, as well as in the middle we've got ALA, which appears twice. But I don't see any patterns that are of length 4 or longer. Now there might be patterns of length 2, in fact there are, but if we're used to the LZ mindset, we might have given up on patterns of length 2 by now. So we saw in the last lecture that in Deflate, you're not even allowed to generate back references of length 2 because it is assumed they are going to be too bulky, that you're not going to get compression with back references of length 2. We talked near the end of the Deflate lecture about the fact that even back references of length 3 might in some cases be too bulky. It might be better just to represent things by literals. And maybe that's just the disadvantage of LZ schemes. But after spending so long thinking about LZ schemes, maybe we've rewired our brains to think about recurring patterns only being profitable if they are 3 characters or longer, or in general, if they are long patterns. In this sequence, we've got a whole bunch of recurring 2-character patterns. Now, I've already pointed out that there are these 3-character recurring patterns, and so it shouldn't surprise us that if I take those apart, so space S and SA, those, of course, will be recurring 2-character sequences if they're part of a recurring 3-character sequence. But let's go through and just take a look at the occurrences of these recurring 2-character patterns. So I've got space S, okay. I've got SA, okay, and we already know that's because space SA is a recurring 3-character pattern. But then we've got AD. So space S, then SA, then AD. And then again, there's space S, there's SA, there's AL, there's LA, and there's AD. Wow, actually, if we begin thinking about 2-character patterns, there are a lot of recurring 2-character patterns. And moreover, notice that a bunch of them overlap. So even if we were looking for LZ-style back references, so for example, if I chose to represent these 2 things by representing the second occurrence as a back reference, then we understand that that means all of these characters have already been handled. The compression scheme, by generating a back reference there, has expunged all of those characters. We don't have to worry about them again. But if I think about these 2-character patterns and I don't constrain myself to the LZ mindset, I notice that I've got this overlapping situation. And maybe some of that overlap is because, for example, for ALA, some of that overlap is actually because I'm actually looking at a 3-character recurring pattern. Or we could say the same about the space SA at the beginning. But even if I were using a Lempel-Ziv scheme and I found the occasion to generate a back reference for space SA, and for the sake of argument, suppose that ALA actually occurred before, so I have 2 different back references I could choose to generate, but they overlap, I'm only allowed to choose one. In a Lempel-Ziv scheme, once I have subjected characters to a back reference, they are gone. I can't have overlapping back references. And maybe because of that, I might lose some potential efficiency. Now, on the other hand, we know enough about the LZ family by now to know that it's already pretty complicated, and there's already a lot of logic involved in finding those back references, so maybe I don't want to introduce more complexity to it. But consider that. Consider, if I think about recurring 2-character patterns, there are a lot of them. And, in general, we might expect a lot of them to overlap. Notice that if we think about other schemes we can use to eliminate patterns, so as far as the usual question we ask ourselves of what can I do to compress this sequence? Well, for this lecture, I want to talk about recurring patterns inside the sequence, patterns of more than one symbol at a time. Obviously, one thing we could do to achieve compression would be to employ entropy coding, so that, for example, the symbol A is more fairly valued, because A occurs more frequently than, I don't know, the semicolon. So we could do that. But what if we're thinking about patterns of multiple characters? Well, we could use the LZ family. That probably comes to mind first. But we could also go back in time and think about other techniques we've used. Well, delta compression doesn't seem, if we go character to character, so from left to right, I don't know how I would apply delta compression to a sequence of text. There are delta compression schemes for text, but not going from left to right. I could think about using RLE, but this sequence doesn't have the kind of patterns that would help me if I used RLE. So notice that in this sequence, there isn't even one occurrence of 2 back-to-back identical characters. So I don't even have runs of length 2 in this sequence, so RLE is not going to have any benefit. I think we can agree by now, having seen a bunch of different ways of condensing multi-character patterns inside of a sequence, that the biggest enemy that we seem to be facing with such schemes is how to tell the decompressor what we're doing. So there actually are a lot of different schemes we could employ, some of which I've only alluded to and haven't discussed in detail, to eliminate multi-character patterns. One that I proposed as sort of a conceptual idea back in lecture number 3 was, hey, if I notice that certain things appear more than once, like space SA, what I could do is send to my decompressor in advance a list of commonly occurring multi-character meta-symbols. So I make up new symbols, and I just send that over to my decompressor in advance. And then when I want to use one of the symbols, I just tell the decompressor this is going to be new symbol number 1. And here's new symbol number 1 again. And then I guess this is new symbol number 2. I could do that. But of course, the problem is, how did I get this information to the decompressor? Maybe I wasted a bunch of bandwidth by having to tell the decompressor my new symbols in advance. And one of the clever, I guess, ingenious things that LZ schemes do is they find some way of combining together, sending over the symbols that appear and reusing them. We just go from left to right. And in the LZ77 LZSS way of doing things, that means that we send the first occurrence of a pattern as regular literals and the second occurrence as a back reference. In the LZ78 or LZW way of life, what we do is send the first occurrence again as literals and send the second occurrence as an index into a symbol table that refers back to a stored copy of the previous set of data. But either way, the challenge is, how do we get the decompressor to understand what sequences we are reusing? And one thing worth remembering is that really the LZ family is a massive family with lots of variations. But if you think about it, pretty much all of the variations are based on how do I encode back references. That's pretty much it. All of the distinctions between the members of the family. So we start with LZ77, and then we branch off and we get LZSS on the one hand. And we know that LZSS is a more compact way of representing the regular back references, the actual length and distance pairs that LZ77 wants to use. We also have the LZ78 branch of the family, which uses a symbol table. But when it comes down to it, a symbol table fundamentally is just a way of storing things for later use. It is a way of caching your back references for later use. So I would argue that really the differences between the members of the LZ family all come down to encoding back references. There are big big differences, like should I use a symbol table versus should I just use a length distance pair. There are also small differences, like if I'm using length distance pairs, should I encode them in that weird bulky triple representation, or should I encode them with a more streamlined representation as in LZSS? But when it comes down to it, the LZ families, the main distinction across members of the family is how do I encode the back references, however I choose to represent them, such that the decompressor can easily recover them and I don't waste too much bandwidth doing so. So that's a big deal. And maybe I guess that points at a larger problem, which is that the schemes we've seen for recycling previously occurring patterns in our string of input have been rather complicated. Not only complicated in terms of defining them and agreeing on how we're going to represent back references or whether we use a symbol table or not, but suppose we've already made that decision. Suppose I've decided to use LZSS and I come to this point in my input. Well, if I'm using LZSS, then I know I'm sending back references using length distance pairs, but wait, do I want a back reference here? I'm standing on this letter A. Do I want a back reference? Well, I guess the first question is there a viable back reference? Okay, so I have to do some kind of search backwards in my data. And I guess maybe I'd find something here. I could search with linear search, I could search with some kind of data structure. And in the previous lectures, all I've been able to give you are a bunch of ideas for data structures that might help. I haven't really been able to tell you, here is a data structure that optimizes finding back references in the LZ family. Instead, I've been able to say, well, here's one that'll get you back references quickly, but maybe not the best back references. Here's one that can represent all possible choices, so you will always find the best back reference, but it could be slow. I haven't really been able to give you something that splits the difference. All I've been able to do is say, here are some things, try your best. Maybe you won't always get the best back reference, but the thing about the LZ family is you don't really have to generate the best back reference or any back reference at all. And so finding back references is tough, and it's complicated and sort of tedious, and it is something where you're sort of hacking away trying to find a compromise between speed and actually getting a good back reference. And even if you do find a back reference, even if it's the best possible back reference, like ALA here, so that's a relatively short distance, and you did find the 3 characters ALA, even if you find it, it could turn out, due to other weird shenanigans, as we saw at the end of the deflate lecture, that this back reference isn't actually worth it, that you're better off just generating the characters ALA. And then there's the matter of, when you're finding a back reference, how long is it going to be? Should I go backwards and look for 3 character back references? Is it worth it to go look for 4 character or 5 character back references? If I have 200 or 300 or 500 or 1,000,000 characters of look ahead, really, there's also the question of how long should I expect my back reference to actually be? And when should I give up? If I find a 20 character back reference, should I go looking for a 21 character back reference far back in time? We don't really have a good answer to any of those questions because all of them are context dependent. And they're dependent on how much time you're willing to spend finding a back reference that gives you an extra 2 bits of compression. And I would argue that part of that is just because LZ schemes are complicated. There are lots of moving parts, and although LZ schemes conceptually are pretty clean, actually implementing them is tough. So identifying and reusing complicated patterns or patterns that occur far apart is really difficult, because not only is there the trade-off between telling the decompressor what I'm going to do, but also there's the matter of, even if I know how to tell the decompressor what I've done, how do I do it? How do I find a back reference? On the other hand, let's think about RLE for a minute. RLE will not help us the least bit on this particular input for now, but if I had an input where RLE would help, so I don't know, here's an input here, A, B, C, and then a bunch of D's in a row, and then an E, and then, I don't know, some C's in a row, and then an A again. Okay, so suppose I'm using just a straightforward RLE scheme, and we've already resolved how the RLE scheme works, so we decided on some way of encoding runs and how long a run has to be before we encode it. We've already decided that, and the compressor gets to this D character. What does it do to decide how to encode the next few characters of text, whether to encode a run or not? All it has to do is look at the next few characters and decide if they're all the same as the one it's looking at. And if they are, it always generates them as a run, as a pair of character and run length. And that means it walks ahead by 5 characters until it hits that E, and then those 5 characters that it found all get expunged immediately. There is no question of how long should I make this run. Should I generate a 3 character run? Should I generate a 5 5-character run. We just walk along with a sort of greedy process and just eat up all 5 characters, and then we are done. Unlike with an LZ scheme where I'm standing on the letter A, and I have to decide, okay, should I look for a 3-character back reference? Should I look for a 4-character back reference? How do I find the back reference? And then if I find it, is it too far back? Is it close enough that it's worth generating? Are literals going to be faster? There are all sorts of questions, whereas with an RLE scheme, it's pretty straightforward. I just eat up all the characters that are the same, and then I am done. And then I move on to the next one. And if you think about that, that sort of means that RLE encoding is basically constant amortized time. Because although, yes, I do more work to find all 5 of these, once I'm done finding them, I just use them all up. So really, I amortize the time I spent finding the run over the characters that I can expunge from my buffer by encoding the run. So RLE is great, but the problem is RLE, a very relatively low overhead, low impact, so high performance scheme, can give us good improvements, but only if we have a very specific style of input data full of runs of consecutive characters. I guess we can call such things obvious patterns. So that's a problem because here's a piece of data, a not very complicated piece of data that doesn't contain those obvious patterns. And so although RLE is nice, it would be great if I could use RLE all the time. I guess I can't on this piece of data because there aren't any obvious patterns. So I suppose then our idea should be, hey, if we think that LZ schemes are too complicated, why don't we find a way of manipulating our input data so that it has more obvious patterns? Because if we can find some reversible transformation, I wonder which transformation I'm going to talk about. If we can find some reversible transformation that gives us more obvious patterns, we can perform that transformation, end up with data that we can then employ RLE on, and then when we're ready to decompress, we just reverse the transformation. So I'll say, here's where we transform, and then I use the inverse transformation. So after I've performed RLE, I can decompress by reversing the RLE, and then I reverse the transformation, and I should end up with my original data. So what I would view this technique as really being, in terms of like the philosophy behind it, is, in a sense, almost a mirror image of what we've already been doing. So the way we've built up to deflate, we talked about entropy coding and things, which is one way of adapting our encoding to the data that we have. So if I want to encode A in fewer bits, in a sense what I'm doing is I'm going to be encoding my symbols into bits, but I'm sort of bringing the encoding to the input. I look at the input, I decide which encoding would best represent the input, so fairly value each symbol, and I bring my encoding to the input. That's one of the reasons we like using entropy coding. But if we think about the rest of deflate, and really the whole rest of deflate, besides all the weird, complicated metacompression stuff, is LZSS, well, what is the LZ scheme really trying to do? Well, we've got this piece of data that has patterns, but they're complicated patterns. They're not obvious patterns. So the LZ schemes, which are pretty complicated, are a way of identifying those patterns. In a sense, we had to come up with LZ schemes, complicated schemes, as a way of bringing our scheme to our data. We have this complicated data, so we need some complicated scheme to accommodate the patterns that it has. We bring our scheme to our data. What I'm suggesting is the opposite idea. I have some schemes that I like. Instead of having some data that I like, I have some schemes that I like. I like RLE. I like relatively simple schemes. So rather than coming up with a complicated scheme to bring the fight to our data, I'm going to bring the data to the scheme. I want to use RLE so badly that I'm willing to jump through hoops to make our data compatible with RLE. So I would view this as almost a sort of mirror image, the opposite way of viewing the world as LZ schemes, and in a sense, sort of making a dent on the logic that went into deflate. Deflate is a bunch of complicated stuff put together in an intricate way. I keep comparing it to a complicated mechanical watch, a bunch of complicated mechanical, carefully machined parts put together in a careful way. What if we approach this from the opposite point of view? I have this data. Yes, the data seems a bit recalcitrant. Yes, it seems like RLE might not help. But that's not RLE's fault. That's the data's fault. I'm going to take the opposite point of view that I took with deflate. And the reason we're doing this is we're building up to talking about BZIP. And BZIP uses a particular transform that might get discussed in this lecture to great effect. You've already seen in this course that BZIP can give us much better performance than deflate in a lot of cases. One other really interesting thing about BZIP is the design philosophy, so sort of reverse engineering BZIP and looking at the underlying design. It looks as if the design philosophy of BZIP is sort of the opposite of deflate. BZIP doesn't do nearly as many of the intricate tricks that deflate does to achieve compression, and yet BZIP outperforms deflate in a lot of cases. Okay, that's something to talk about in the next lecture. The idea in this lecture is to find some transformation that takes arbitrary data and hopefully manipulates it in a way that allows us to employ simple compression schemes and not complicated ones, but still get good compression. And the one I'm going to suggest is the Burrows-Wheeler Transform, or the BWT for short. As I mentioned at the beginning, we have to distinguish in this lecture between the forward transformation, so I take my input data and produce the BWT representation of that data, and the inverse transformation, the inverse BWT. So of course, we'll talk about the forward transformation first. The BWT is a transformation of a string of data. And one of the great things about it, which we'll see in a few minutes, is that if you give the BWT an input with recurring 2-character patterns, the result, the transformed representation, will have runs of consecutive characters, or will likely have runs of consecutive characters. We'll see later that it doesn't always arrange all of the identical characters into a run of consecutive characters, but in general, BWTs can be expected to produce runs of identical consecutive characters, which means RLE can now go to work on the output of a BWT. The BWT is a block-based scheme. It's a block-based transformation, which is, of course, block-based compression is sort of the opposite of streaming compression. We've already seen plenty of cases where we do compression in sort of blocks at a time. So for example, the deflate scheme is a block-based scheme. We have to choose a block type and then encode each block separately. The key thing to understand is we're allowed to use block-based compression in this course and still obey our streaming requirement from lecture 2. The key thing is we have to make sure that our blocks, if I choose to encode a specific chunk of input at a time, I have to make sure that block's size is fixed, bounded above by a constant. So I'm not allowed, if I want to do a block-based transformation like BWT, I'm not allowed just to read in all of my input at once, whether that be 1 megabyte or 20 megabytes or a gigabyte or a terabyte. That wouldn't be allowed. I am allowed to process blocks at a time, but I have to choose my blocks to be a constant size. So I could choose a block of 10K, I could choose a block of 1 megabyte. We'll see, and it'll be sort of, maybe it'll be intuitive why this is, but the BWT tends to yield more benefits the larger the block is. But we're allowed to use blocks and still obey our streaming requirement as long as the blocks are limited to some constant size at most. So compression schemes that leverage the BWT will process a stream of data by saving up a certain number of characters at a time and then breaking the character into turning that into a block and then running the BWT on that entire block. So as far as BZIP is concerned, and we'll talk about BZIP in great detail in the next lecture, BZIP uses blocks of size between 100K and 900K, depending on settings. And I'll talk about what the settings are in the next lecture. But just for a sense of perspective, I'm about to perform a BWT on this relatively short input. It is very, very short compared to even the smallest block size used by BZIP. BZIP would use a block size of 100 kilobytes, so about 100,000 characters at a time. And I think that's important perspective to have at this point, because when you see the next step of the BWT, you'll begin to chafe at the idea of applying such a step to a 100,000 element sequence. Okay, so what's that next step? Well, the first step, I guess, to perform a BWT is we take our input sequence, and then the input sequence contains n symbols. So there are n total characters. It has length n. The first thing I do is I construct an n by n matrix of characters. And then I set the first row of that matrix to be my input string. So an n by n matrix. So if I have a sequence of length n, I am already using n squared space to store this. Now, we'll spend some time later in the lecture thinking about ways to avoid using n squared space, but for the sake of demonstrating the transformation, we need this n by n matrix. Now imagine if it's an n by n matrix where n equals 100,000, or where n equals 900,000. Well, 900,000 is not a big number in the context of this course, but 900,000 squared, yeah, finally, I'm willing to concede that is a pretty big number. So we probably want to avoid that. And that's one reason why we don't use larger block sizes. Now, if you were to design a scheme based on the BWT in 2023, you might use a larger block size than 900K. But that might have been a limiting factor when BZIP was designed in the mid-1990s. Okay, so step one, we fill in the first row of our matrix with our regular unmodified input sequence. And then we construct the remaining rows of our matrix by performing cyclic shifts. I'm going to use the word rotation for this. So the idea behind shifting a string, you might remember from first year programming, a very common, like just a ubiquitous first year programming exercise or exam question is, here is an array, shift this array one element to the left. So a shift of a string, in my opinion, is where we take the string and we move each character over. So this space moves one character to the left, this S moves one character to the left, so does the A, and so on. Notice, though, if I move every character to the left, this character, the first character, gets knocked off the edge. So I want to perform not just a shift, but a cyclic shift. Again, I'm going to use the word rotation for that. So a rotation is a shift where after I push everything one character to the left, the character that gets knocked off the end, it gets brought back and occupies the last position. So the last character got pushed over to the left, which leaves a gap here. So a cyclic shift is where I bring the first character back and I insert it into the last character of the next of the shifted array. So I rotate the string around by one character. So step two of the BWT is I fill in the remainder of my n by n matrix by taking the first row and shifting it one character to the left. And then I shift it, the row 2 will be the first row shifted 2 characters to the left. And then row 3 will be 3 characters to the left, and so on. I can also achieve the same effect by first shifting row 0 by 1 character. That gives me row 1. And then to produce row 2, I just shift row 1 by 1 character. So to produce any row, so if I wanted to produce row 8, I could just shift row 7 by 1 character, whatever. Either way, when I'm done, what I have are the set of all possible cyclic shifts of my original string. And you'll notice as a result that row 1 starts with a space. It starts with the character in column 1 of my first row. But for example, row number 12 will start with the space from column 12. And row number 13 starts with the A from column 13. So actually, as a result of performing all of these shifts, every single character in my input string gets to take its turn being the first character of one of the rows, because it is the beginning of one of the shifted versions of the string, once I've generated all possible rotations. One other thing you might notice is as a result of doing that, because the first character of row 1 will be the character at index 1 of my original string, and the first character of row 2 is the character at index 2 of my original string, that actually means that if I walk down column 1, I should see a complete copy of my original string. And I do. Notice how it is, the walking down the column is the same as walking across the row. And actually, what this means is that the entire matrix will be symmetric. It's symmetric in a lot of interesting ways. One thing you'll notice is that if I look at the back diagonals, they'll always be exactly the same character. But the matrix is symmetric. So at this point, it turns out it won't be symmetric for long because I'm about to modify it, but at this point, that means the contents of column number 2 are going to be the same as the contents of row number 2. So every possible rotation of my string is now stored in one of the rows of this matrix. And because every column because of this symmetry property, every column actually also contains one of the rotations of the string. So for example, the rotation that I can find in row 1 is also going to be in column 1. Now I'm about to rearrange the rows, so that's not going to be the case in a minute. One observation I want to make, though, is because every column contains a rotation of the string at this point, that means that the collection of all possible characters in the string will be the same collection that I find in every column. So every column contains every character that was in the original string. Even if I reorder the rows, that will still be the case. If I don't modify if I don't change the ordering of columns, but I just reorder the rows, every column will still contain the same collection of characters that my original string had. Okay, step 3. I take all of the rows of the matrix. I don't modify the contents of the row internally, but I rearrange the order of rows. I rearrange the order, so basically we can view this as if I treat each row of the matrix as a separate string, I then rearrange the matrix so that those strings, the string corresponding to each row, those strings have been rearranged to be in ascending order. So they are formally, we call that sorting them lexicographically. You can think of it as being sorted in dictionary order or as being sorted alphabetically, but we have to generalize alphabetical order to arbitrary symbols. So notice that all of the rows beginning with A are now together, and internally they are sorted alphabetically. So it turns out that in the normal character comparison that we're going to use, which is ASCII, the space character comes before any uppercase letters. So space, and that's why space sorts to be earlier than A. But notice that among the various rows that begin with A, the second character being space, well, that row will have to come first. The two rows that have AD will come before the rows that are AL, and the row with AS comes after everything else because I'm sorting everything into lexicographical order, and that's very important for later. We're going to need to leverage that property later. Now, when I do this sorting operation, the original string will move. Probably. I mean, maybe it won't, but it probably will. So what I have to do is keep track of where my original string ended up. It began at index 0. When I was done sorting, it is now at index 4. So I make a note of that. I'm going to do that via this blue highlight here. All right, step 4. After I'm done sorting the rows, I go and grab the last column of the resulting matrix. So I'll highlight that in orange. And then the BWT is the combination of the data from the last column in order, so you can see there, we'll call that last column data, as well as the index where the original string ended up. So the BWT is a pair of information. First, it is the contents of that last column, and second, it is the index where the original row ended up after sorting. So for my original input string, the BWT would be this thing, and then the index 4. Now, a natural question is, hey, if I'm only going to keep one column of the matrix, which is sort of nice because if I save only one column of the matrix, that means that the resulting data will still be n characters in length and not n squared characters. A natural question is, hey, if I'm only saving one column of the matrix, why is it the last one? The first column had a lot of nice properties once I was done sorting. Here's the first column. I'll come back to this in a minute. Why the last one? It turns out you don't necessarily need to store the last one, I guess. But storing the last one has a lot of benefits, and we'll come up with those in a few minutes. I want to justify that because it does seem like it comes out of nowhere. So I'll come back to that. In the meantime, I want to look at the BWT a bit. So here's my input string, and here's the BWT. As I mentioned at the beginning, this input string had recurring 2-character patterns, like space S, SA, AD, there's space S again. It actually has recurring 3-character patterns as well. And the input string did not have any instance of a run of 2 or more characters in a row. So RLE couldn't do anything with the input string, but take a look at the BWT. I now have cases of 2 characters in a row. Okay, runs of length 2 aren't always the most exciting, but there they are. I went from having no runs of length 2 or greater to having some runs of length 2. And, oh, there's another run of length 2. And I now have this run of 5 A's. So the BWT somehow, on this input, I don't know whether you want to believe this in general just yet, the BWT on this input was able to create a manipulated version of my data that RLE now can actually make some progress on. What's especially interesting about this is this was a pretty small input, and if you want to take my word for it that the BWT has this effect, then we should expect this effect to be amplified if my input gets longer and longer. So if I have at least one run of length 5 out of an input that was pretty short, I might get some pretty good results, some pretty long runs showing up if I use a longer input. For example, an input of size 100K. I want to talk a bit, I guess, about justifying the property I just observed. Maybe this is just a coincidence. I mean, if I randomly reorder these characters, maybe I'll end up with 2 A's next to each other. So how do we know the BWT actually achieves this effect in general? I want to try and justify that. And then I want to talk more about that whole last column versus some other column business. Basically, the idea behind the BWT is when I take my input string and I generate all of the possible rotations, that means that there's going to be some row of my matrix that begins with this character. So I'm cutting off the string here. This becomes the end of the row, and this becomes the beginning. And if you think about it, if my string has a lot of recurring patterns, so let's take a look at the pattern AD. Okay, so both of these D characters get their turn to be the beginning of a row. That means I'm going to cut off the row between the A and the D in both cases, which means that the A will become the end of the row that begins with the D. So both of the rows beginning with D will end with A. And furthermore, if we look at the rows that begin with D, what do we know about them? So there are going to be 2 rows beginning with D. Okay, so there's going to be one row that begins D space and one row that begins D semicolon. Okay, and we just saw that if we cut the row off so that D can be the beginning, those rows both end with A. Now notice, when I sort all of the rows of the matrix, the two rows beginning with D will always be next to each other, or they'll be nearby to each other. Rows beginning with the same character will be nearby because I've sorted them. And that means there's a pretty good chance that those two A's will be next to each other in the last column. And that is what I'm observing here. It's those recurring two-character patterns. Notice that there were quite a few recurring two-character patterns that began with A in my original input. So there was AD, there was AL, there's AD, there's AL, and there was also AS. I don't think AS was one of them. So there were lots of patterns, recurring patterns that began with A. Actually, there's SA that shows up more than once. SA actually shows up wrapping around the string, but it also shows up in all of these places. There are lots of patterns that involve A's, and so it shouldn't surprise us that much that if I cut off all of my ALs and ASs before or after the A, that a bunch of A's are going to end up next to each other in the last column. So now let's consider, let me just redo that sketch with an actual BWT. Let's consider a string that contains repeated occurrences of the pattern WAS. And this is a three-character pattern, not a two-character pattern. But any three-character pattern that reappears is actually just two-character patterns that overlap. And I want to use this three-character pattern example deliberately to illustrate that, unlike with LZ schemes, any two-character pattern, even an overlapping two-character pattern, so a long pattern that's a bunch of overlapping smaller patterns, can still bring us huge benefits inside of a BWT, because the BWT only cares about two characters at a time, the character in the first column and the character in the last column. It's all about where do I cut the row off? Which character becomes the last one, which character becomes the first one. So here's, I'm going to use this string. The word was 4 times, but separated each time by a different character. So the reason I've added the uppercase A, uppercase B, uppercase C, uppercase D, which only appear once inside the string, is that by doing so, I avoid creating more complicated patterns. If I just had the word was 2 times back to back, now there are actually patterns like ASW that reappear. I just want WAS to reappear. So I have this string where I've deliberately added these sort of spacers to avoid creating any more patterns than I want. Now, if I generate the BWT matrix, notice that every character gets its turn being the beginning of a row. Because uppercase letters sort to be lower than lowercase letters, the rows beginning with A, B, C, D are up here. Now, as far as all the other characters, in my original input string, which is this, there are 4 occurrences of the letter W. I can start the row with the actual letter W at the beginning. I can start it with the letter W after the uppercase A. I can start it with after the uppercase B, after the uppercase C. All of those rows end up sorted together when I'm done. If I take a look at, let's just draw the word was here. If I cut it off before the lowercase a, well, all of the lowercase a's in the original string get their turn being the beginning of a row. But all of those rows end with a W, because, of course, the A is part of a recurring pattern, WAS. So if I cut the row off to begin at the A, those rows will all end in a W. Because the matrix is sorted, all of the rows beginning with A end up together, and that means all of those W's end up together in the last column. And so you can see that although, just like our earlier example, this input has no instance of 2 characters consecutively, 2 identical consecutive characters, when I'm done the BWT, I've got these nice blocks of S's, W's, and A's. I'm not guaranteed that every occurrence of A will be right next to each other in general, although that does happen here with all of my lowercase a's. But in general, when I have these recurring 2-character patterns, the BWT is really good at batching them together into runs of consecutive characters, which is great because it means I can then put RLE to work, and RLE can actually get some results. So when I break that word was across the table boundary into W at the end and AS at the beginning, all the A's and S, all the strings beginning with AS get sorted together in my matrix, and that means all the W's are together, which means when I take the BWT, which would be this, the last column, I can use RLE. And so this clustering behavior is I think the ingenious factor that makes the BWT so powerful when combined with an actual compression technique. Because remember, the BWT itself isn't compression, it's a transformation. And so these repeated runs of characters, I hope that those examples were enough to convince you. The repeated runs of characters we saw in the earlier example weren't a coincidence. That wasn't just good luck on my part. That is because the BWT is really good at doing that. By slicing the patterns up, it is really good at producing these runs of consecutive characters in the last column. And that property makes BWT output a really good candidate for things like run length encoding, which are a pretty low impact and low overhead scheme for condensing down runs of the same character. Now, then there's the question of, wait a minute, if all I want are runs of the same character, why not use the first column? Like, why was it that I'm taking the last column? That seems quite a ways away from the most comfortable part of the matrix, which is the beginning. Especially because if you look at the first column, you can observe that because I've sorted all of the rows, then all the rows beginning with A will be next to each other, and all the rows beginning with D will be next to each other. So if I was allowed to just use the first column, I'll have even more runs of the same character. So contrast the last column where there are runs of A's, but not every A is part of the same cluster. There are cases, and same thing with the space. There's a cluster of spaces, but there's this other space sort of sitting by itself. And the letter L never gets to be part of a run of consecutive characters because there are two L's and they are kept separate. Okay, well, that's too bad. Whereas if I look at the first column, everything is stuck together. So why don't I compute the BWT and just save the first column? I think that's a natural question to ask. And I think maybe you've concluded by now the answer must be related to the fact that it's impossible. There's something about the BWT where if I save the first column, the properties I want, even if runs of characters are present, something would break. So let's take a look. Here's the string. My input string, as we recall from earlier, is a sad salad, alas. Now that's based on a true story. I'm a big fan of salad, but a sad salad's never very much fun. And it turns out that if I take the first column, I will not be able to recover my original string. So if my BWT was just the index where my original string lived and the first column of the matrix, then I would not be able to recover the original input in all cases, because the first column contains all of the characters of the string in sorted order, which means if two strings contain the same collection of characters, the first column of their BWT matrix will always be the same. So here I've got a sad salad, alas, and here I've got a salsa dad, alas. I don't know if that's based on a true story, but it would be an interesting story, I guess. And this is exactly the same. If you look at the first column of the BWT matrix, it is exactly the same in both cases, because these two strings are anagrams of each other. They contain exactly the same set of characters. So I can't save the first column. A question that we should ask then is, wait a minute, so how do we know we can save the last column? Now it turns out in this case, for this second string, the last column is distinct from the last column in the previous example. So this isn't a counterexample to my claim that we can save the last column. But you should be asking, if I've given you a counterexample for why we can't save the first column, how do I know that I'm always able to work backwards from the last column to recover the original string? And I will demonstrate that point to you in a few slides. I want to talk a little bit, though, in the meantime about how you would implement this. So the process I described, for the sake of understanding the BWT, requires this n-squared matrix. I would rather not work in n-squared time if I can avoid it, especially if the value of n is 900,000. I do not want to work in 900,000 squared operations if I can avoid it. But even if I have to deal with that, I really, really don't want to use this amount of memory. I do not want to use n-squared memory because although I'm impatient, in general, as time goes by, I'm less and less patient with my computer programs, to just get stuff over with and be done. I am willing to wait a long time for my program to be finished. I am not willing to go out and buy more memory. So my computer has a finite amount of memory. Although my patience is also not finite, I can always wait a bit longer for programs to finish. There is a limit on how much memory I can consume. I don't want to have to actually construct a matrix of size 900,000 squared. So what do? I want to talk about how to compute BWTs faster. So not by actually explicitly creating a matrix of n by n characters and sorting it. I want to talk about at least one improvement I could make that would improve the space complexity, if not the time complexity. There are actually improvements we'll see later. It is possible to compute a BWT in linear time. So linear time implies linear space with a more complicated algorithm, one that we don't have time for in this course. So suppose I want to compute my BWT without creating that n by n matrix. What I could do, instead of creating the n by n matrix, is leverage this property that actually every row of the matrix is pretty similar to every other row. Really, every row of the matrix is one of the other rows, but just shifted slightly. So that means every row contains exactly the same sequence of characters in the same order. I just start and end the sequence in different places. So one way that I could save some space is only actually store the sequence of characters once, and just, instead of actually explicitly storing the matrix, I could essentially store a list of directions to where each row starts, where in the sequence each row starts. So for example, in this matrix here, this row begins at this character in the original sequence. And this row here, the one before space D, begins at this character in the original sequence. So if I tell you where I'm starting the row, you could just recover, and you have the original sequence. You can recover the entire row by just walking to the end of the row and then from the beginning of the row to where you started. That would give you the entire row. So actually, I don't need to store the entire contents of the matrix, just one copy of the original sequence and a bunch of pointers representing directions. So the way I will represent this is I will treat my original string as a circular buffer. So the idea basically being if I walk off the N, so the character after the A is the G, and the character after the G is the U, and then the U is the A, and so on. But we'll treat this sort of like an array that I can index into at index 5 or 6 or 7 or 8 if I want to. And if I get to an index above the actual length of the input string, I just wrap around. So I can do that. There are a variety of ways I could abstract that in code. Hopefully you see what I mean. And then I represent my matrix. This isn't the matrix itself. This is just being used as a some sort of backing storage. My matrix is then this structure, which is, and I've drawn it vertically, but it's just a one-dimensional array of pointers. And the idea is the pointer at each element represents one row of the matrix, and the pointer just tells you where the row starts. So in other words, let's take a look at row number 2 here. When I say row number 2 starts at this character A, what I'm actually saying is row number 2 is A, V, A, G, U. Because I just start walking at the A, V, A, and then I wrap around G, U. We know in advance how long each row is going to be because the string has 5 characters, so every row is length 5. And so I can use this array of pointers to represent all of the rows of the matrix. And each pointer has a constant size, so I'm now down from having an n squared data structure to having a big O of n data structure, because I've got n space for the original string and n space to represent all n pointers. And then to perform the BWT, so there's my matrix as of, I guess that was step 2. I've constructed the matrix. Step 3 would be to sort the matrix. Well, because I can recover, if you give me any index of this table, I can get the row for that, in that row of the matrix, so A, V, A, G, U, which means that I could treat this as if it were an actual table of strings. I just have some abstraction required to, when you want the string corresponding to a particular row, go and generate it dynamically based on the sequence, based on the circular buffer. I can then sort the array based on that. So what I'm doing basically is sorting the array of pointers. And the comparison condition, if I want to compare, I don't know, let's do these two. So suppose that while I'm sorting, I want to compare this index with this index here. Okay, well that means that row 1 is A, V, A, G, U as before, and row 2 is G, U, A, V, A. And when I compare them, of course, this comes out as being lexicographically smaller. And row 0, when I'm just to illustrate further, row 0, which is the string A, G, U, A, V, well, that is lexicographically smaller than A, V, A, G, U. So I am able to perform the sorting. It's just that whenever my sorting algorithm has to perform a comparison, assuming I'm using a comparison sort algorithm, whenever my algorithm has to perform a comparison, I have to give it a comparison function that actually generates the necessary row and performs the comparison. So it just walks through, starting at each pointer, it just walks through the appropriate string and compares each character one at a time. We know, of course, from some previous course that if you want to sort something using a comparison sorting algorithm, you can do it in n log n total comparison. So big O of n log n time multiplied by the runtime of each individual comparison. And that's where things get a bit unpleasant. So in the worst case, we could end up having to compare rotations of a string. So consider a string that contains a very large number, let's say this one here, a string that already contains runs of the same character. So this string has length 7, and the first 5 characters are A. And that means that there are going to be rotations that look like this. And then we'll do one more. We've got, I think it's that. So rotations will look like this. Now, the problem is when I go to sort these, if I'm comparing these two strings here, the comparison has to walk pretty far into the string before it hits two characters that are different. When you're comparing two strings, you can bail out. Like the comparison is over as soon as you find two differing characters, as soon as you find a column where two characters differ. The problem is you may have to walk through a bunch of columns where the characters are the same. And we won't worry about exactly how we work out the bound here, but it is possible for that to take big O(n) time in the worst case, with a set of rotations. With a set of arbitrary strings, of course, if I compare two strings that are exactly equal, so if I look at the set of rotations of this input here, every row of the matrix is going to be exactly the same, which means if I attempt to compare two rows of the matrix, I'm comparing these two equal strings. To determine whether strings are equal, you have to look at every single character, which of course is going to be big O(n). So that means that if you have a bad input, and of course if we talk about worst case analysis, you sort of assume you always have a bad input. If you've got the wrong input, that means that performing the sorting operation will require big O of n operations per comparison. So if there are n log n comparisons, your total running time is n squared log n, which is too bad, I guess. That is the same running time as if the matrix were constructed explicitly. However, you only need big O and n space. So this is still an improvement. And I will add that unlike in the matrix-based version, where you're always using n squared space, and therefore you always need n squared log n time to move everything around the matrix, in this version, the worst case of n squared log n only happens for certain inputs. So if we think about the expected case, it's probably going to be quite a bit better than that. We probably could get down to n log n in the expected case. So this, and I've actually implemented this, so I've used this mechanism to compute BWTs in my own implementation of the bzip encoder, and I've discovered that, yeah, on average, the runtime is pretty manageable. And actually, it turns out, we'll see this next time, but it turns out that in the bzip encoder, there is a pre-processing stage before the BWT whose original purpose, although it turns out it was not really needed, the original purpose of one of the stages of the bzip pipeline is to manipulate the input data in such a way that it's less likely to have that worst case behavior. So one way or the other, if we use this representation, we can get the running time of the BWT down to a manageable time and a manageable amount of space in most cases. And so this worst case behavior gets avoided if you have a string that has a decent amount of variety, basically. If different rotations tend to different early characters, that is, the string doesn't contain long runs of the same character, then you likely won't have the worst case behavior. What's amusing about this is the result of the BWT is primed for RLE. If you happen to feed in something that already is primed for RLE, so that is the same character over and over again, then the BWT actually takes longer to compute in this version. Okay, just for completeness, once I'm done the sorting, I can then recover the BWT itself, which is the last column of the matrix, by using my sorted array of pointers. So remember that the pointer points to the first character of the row, which means if I want to retrieve the last character of the row of the matrix, I would just follow the pointer, and then, so for row 0, I follow the pointer and then just walk back by 1. So that means that the last column would be, okay, so for row 0, it points to A, so the last column would be V. For row 1, it points to this A, so the last column is U. For row 2, it points to this G, so the last column is A. For row 3, it points to the A, so the last column is... for row 3, sorry, it points to the U, so the last column is G, and for row 4, it points to this V, so the last column is A. So if you just walk one step backwards from the pointer, you can easily get the last column, and then you get the BWT. It turns out you can compute the BWT in linear time using something called a suffix array. Suffix arrays are really interesting. There's a related thing called a suffix tree, and they're sort of interchangeable. You can go from one to the other pretty quickly. That's a topic that could eat up like a month of an algorithms course. I don't have a month to spend on that as much as I might want to do that. It turns out that once you have a suffix array, you can compute the BWT in linear time from it. It also turns out that you can create a suffix array in linear time, which means that if you put those two pieces together, it is possible to compute the BWT in linear time. So although the computation is more complicated than this one, it will give you a better asymptotic time. You avoid that worst case behavior. Now there's the question though, okay, so I can compute a BWT. The BWT is interesting. It's got properties that lend themselves well to compression, but can I reverse it? I mean, if I can't, if you give me this scrambled set of characters and I can't recover the original input, then this is useless. Obviously, I need to be able to invert it. Ideally, I want to be able to invert it very quickly. I don't want to need that n-squared matrix to invert it either. So our task is invert the BWT. I want to recover the original string. And to approach this, I'm going to start by going back to the matrix because it helps us to work with the matrix, I think, to visualize things, and then I'll talk about a way of making it fast. So for now, I will ignore the efficiency concerns. Let's go back and talk about the BWT in its full matrix-based form. So the BWT is this sequence, R, G, N, A, E, O. Okay, so I guess what I'll try to do, my approach here will be, I will try and recover every single entry of this matrix. If I can do that, then I can get the original string. That will be my approach. So at the beginning, I have managed to deduce the last column because you gave me the last column. That was the BWT. I also know what index I should expect my original string to appear at once I'm done recovering the entries of my matrix. I also know the first column though, because remember that the first column is always going to be the set of characters in the string, that is to say this set of characters, because every column contains the complete set of characters in the original string. The first column is the set of characters in the string sorted into ascending order. So if you give me the last column, all I have to do is sort the last column and I get the first column. Okay, so I get 2 columns for free. You give me one and I can recover the first column easily. Earlier I said, why do we choose the last column? Why not the first column? Well, we agreed, we now understand why we can't choose the first column because the first column would result in ambiguity. But also because if I give you the last column, I can easily recover the first column from the last column. It turns out, I suppose, that you could actually frame the BWT not in terms of the last column, but in terms of like the second column or something like that, as we'll see in a minute. But using the last column has a lot of benefits, and that's one of the reasons they made the choice they did. This is actually an example I should add. The BWT is an example of a pretty ingenious scheme. I really would like to see, I'd like to get inside the heads of Burrows and Wheeler when they were inventing this. The end result is so ingenious that I really want to find out how they came up with it because it's so clever. So the question is, if I know that I get these 2 columns for free, what else can I deduce? And it's cheating to look at the string and try and go find English words that have these characters. If I know nothing about the input string and I don't know anything from an English dictionary, what else can I deduce? And what I can observe is, remember that this matrix was computed by taking cyclic shifts, which means really this character comes before this character, and this character comes before this character, which means I actually know quite a bit about this next column, column number 1, even without having it explicitly. So I could observe, for example, that if E comes before O, well, I guess that means O goes after E, which means this thing must be an O. And if G comes before E, well, that means that this must be an E. So I actually can deduce a lot of the elements of column 1 based on what I know about the last column and column 0. And I can do that maybe as a way of visualizing it more clearly. What I'll do is, so here's my actual matrix, columns 0 through 5. What I'll do is I'll add a sort of phantom copy of column 5 to illustrate the cyclic property of this matrix. So that means R comes before A, or A comes after R, E comes after G, G comes after N. And I can leverage those observations to fill in column 1. So if I notice that R comes before A, or A comes after R, then that's a 2-character fragment of my original string. Somewhere in my string was an R followed by an A. Well, in column 0, there's only one R, so I guess the A has to go here. Okay, so I can deduce that. I can fill in that entry. And I can do that for everything else as well. If the string contains GE, there's only one G available in column 0, so this has to be an E. And I can do that to fill in all of column 1. Okay, so now what do I do for column 2? And maybe you can see that really, if I have any two adjacent columns, so column 5 and column 0, because the matrix is cyclic, there's nothing really that special once I have two adjacent columns about which two columns they are. I now know pairwise relationships inside of my input string, so once I have column 5 and 0, I can fill in column 1. Once I have column 0 and 1, I can fill in column 2. So I can observe, for example, that apparently n comes after a. Okay, so that means that there's only one A available, so in column 2, this thing has to be an N. Okay, E comes after G. Wait a minute, E comes after G. Didn't I already say that E came after G? Oh yeah, that's right. I don't even need column 1 to recover column 2 that much. All I really need is this relationship that G comes after N. And then I guess I only need column 1 for the sake of anchoring where the N is. But in terms of which character comes next, all I need is the relationships between column 5 and column 0. That's going to be significant later. Once I have column 1, I can build column 2 by recycling all the observations I made when I built up column 1 and just tacking them on to column 1. So I can use that to recover column 2, then column 3, then column 4. And once I'm done, I have my original string, which was the word orange, which occurred at index 4. So I used my last column, and eventually I had to use the index of the original string, and I was able to recover the entire matrix and therefore recover the original string. Okay, great. So I've managed to reverse my BWT by deduction. The problem is that deduction process isn't really an algorithm yet. That's just me playing around and identifying relationships. There are a couple of loose ends, and I wouldn't really be surprised if you were a bit skeptical. You're looking at this and saying, okay, so I was able to solve this puzzle by hand without any particular rigorous algorithm for this input. Does it work if I've got 900,000 characters in my string? And even if it does work, can I do it quickly? So basically I have to address, first, how do I reconstruct strings where it's not as obvious? Because maybe this was just a lucky input because each character occurred only once. Recall back when I was reconstructing column 1, the logic I used in most cases was something like, oh, I know that G comes after N. And that means in column 1, there has to be a G somewhere, and there's only one N, so it has to be here. What if there were two N's? What if there were two G's? In that case, maybe it's not as obvious. So I have to somehow address that. I'm going to do that with a bunch of other examples. So that's one thing. How do I reconstruct strings where the same character occurs more than once? And then, how do I perform the reconstruction quickly? So certainly I want to do that in less than n squared space. I also would really rather not do it by generalized deduction, because having to do it by deduction of just solving the puzzle by hand could translate to a very slow algorithm. And so the reason these are significant is, of course, because to get the benefits of the BWT, I want there to be lots of recurring two-character patterns, and to have lots of patterns, the easiest thing to do is to have lots of data. And so if my BWT is being taken on hundreds of thousands of bytes at once, I need some way of quickly inverting it. So I want to be able to invert it in less than n squared space, certainly. I want to be able to invert it reliably, so that it has to be invertible. Ideally, I can invert it in like linear time or n log n time. All right, let's try this one. Here's an example with a little bit more ambiguity. Notice how the same characters occur more than once. There are actually 3 P's and there are 2 E's. So maybe my deductive process will be a little bit harder. It turns out it won't. It turns out that if I leverage properties of that matrix, I can still reconstruct the matrix. Okay, so this won't be as straightforward, but hopefully I can still do it. So I've just, like before, I've reconstructed my matrix to the point that I have it. So I've got my last column, I've got my first column. I've built in my phantom copy of the last column to allow me to make these deductions more easily. And let's see what stuff I can come up with here. Okay, so let's see. E comes after N. Okay, that might be easy because there's only one N, so the next character has to be an E. E also comes after L. Okay, well, there are 2 E's, but it's pretty clear that they occur in distinct context. E comes after N, E comes after L, so that means this is an E and this is an E. Okay, what else do we have? I comes after P. Okay, but there are 3 P's. Okay, L comes after P. Okay, still, there are 3 P's. Which P are we talking about here? Okay, so there is clearly a little bit of ambiguity. If something comes after P, I have to know which P I'm talking about. So it comes down to this question, basically. I've got 3 P's sitting in in columns rows 6, 7, and 8, there are 3 P's beginning the row. I know from looking at the relationship between column 8 and column 0 that my choices for these 3 characters are PI, PL, and PP. Those are the 3 things that can follow a P, I, L, and P. The question is which one goes where? So some combination of P, L, and I have to appear in these 3 rows because P is followed by I, L, and P. The question is which order do I put them? And it turns out this is not ambiguous. We can resolve this. The way we resolve it is remember the properties of the matrix. In this matrix, at this point, the rows are sorted lexicographically. That means that this string here has to be lexicographically less than this string here. Or I guess they could be equal, but less than or equal to the string below it. So I think if this were PL and this were PP, would that work? Well, yeah, in this case, sure. PL comes before PP. If this is PL and this is PP, then I guess the next one has to be PI. Would that work? Well, no, because this string is lexicographically smaller than this string or this string. So actually, the ordering of I, L, and P is implied. I have to put them, I've got 3 choices, I, L, and P. I have to write them down in ascending order. I first, then L, then P. That's the only way it works, because in any other arrangement, these 3 rows haven't been sorted, and that wouldn't be allowed. In the original matrix, they were sorted. So I comes first, then L, then P. And the same thing actually holds for the E's. So there are 2 things that can follow an E in this example. We've got EA and EP. But if I put EP before EA, then the sorting criteria would be violated. EP is lexicographically larger than EA, which means it's unambiguous. The A has to come first, and then the P. Now, you might look at that and say, maybe that was too easy. Maybe the ambiguity wasn't severe enough for me to distinguish. Maybe I already know what word this is, and therefore I'm just working ahead. Okay, how about this? Here is an input that is pretty obviously going to be not an English word. This is a much more cryptic looking input. What do we do in this case? So notice how there are 4 A's, 4 B's, and 1 C. And if I look at what can follow, well, okay, let's, I guess, start with the A's. What can follow an A? So I've got the following pairs. I've got AA, AB, AB, and AB again. So that would be these 4 pairs here. AA and 3 ABs. When I'm filling in these 4 rows, what order do I put them? Well, it makes sense to me that the AA has to come first, then the 3 ABs. There are multiple ABs, but they all would have to appear after the A because the rows have to be sorted. They have to be lexicographically sorted. Now, among the ABs, what comes after the Bs? Well, again, when I fill in what comes in column number 2 here, I'll have to fill it in so I retain that lexicographical ordering. Okay, so how do we do this? Well, actually, I've gotten a little bit ahead of the slide, so I'll just cut to the chase. I know that because these 3 rows are tied, I have to fill in the character in column 1 to retain that lexicographical ordering. So I'm required to do I, L, and P in that order. And then similarly with the E's, A and P. I can deduce the remaining characters using a process relatively simple like what we did in the previous example. And then what about this cell here? Okay, so after PP. Well, there are a couple of ways of addressing this. So how do I recover column 2? Because again, there's the question of what comes after a P. We know that P can be followed by I, L, and P. Well, there are a few options. One option is just to say, hey, wait a minute. I have 2 characters of the row already, PP. What comes after a PP? Well, there's only one choice at that point, and it's this, PPL. So I can use the fact that I now have 2 characters of the row. I can bootstrap myself into getting the 3rd character more easily by leveraging the data I've already been able to recover. And by this point, there's actually enough to recover the entire matrix, and the word is pineapple. Now, I can actually perform that inversion without reconstructing the full matrix. So just like before, it's good to use the matrix as a visualization tool, but we do not want to construct an n-squared matrix in practice if we can avoid it. The thing I will observe, the overarching characteristic of the logic that we just used, all of our deduction logic, is really all we're doing is saying, if I'm standing here, if I'm at this point in my original string, and actually we know if we're at row 6, this is actually character 0 of my original string, what comes next? If I'm at this point in my original string, what comes next? This is the beginning of a row, but we know that every row is actually just the beginning of a certain rotation of the string. What character comes next? Well, okay, so we know that after the A is going to be a P. Okay, so that means that after the A, I go to one of the P characters. I think it turns out it's this character here. All right, so after the A is the one of the P characters, or actually, no, after the A is this P character. Sorry, I drew the arrow wrong. It's this one here. Okay, what's after the P? Well, it's going to be one of the either I, L, or P. But you might notice that really what we're doing is not actually filling in individual characters of the matrix. I mean, although that's edifying, although it's easy for us as humans to see that, all we're actually doing is deciding after each character, what row am I in next? So I go from the N to this E. Okay, so I go from the E to, in this case, let's see, the E would go to the A here, or I'll draw the arrow better. But really what I'm doing is just making up pairwise relationships between individual elements. And so what I could do, instead of actually filling in the contents of the matrix, is I could just make that mapping explicitly. So here what I've done, this is for representation purposes, I have just drawn out 2 copies of column 0. So column 0 is in sorted order, and then before it, in both cases, I've made a phantom copy of column n-1, the last column of the matrix. What I'm basically going to do here is just figure out, okay, what comes after this A? That's all I need to worry about. And I can deduce that it's followed by, the first character, this A, is followed by a P character. That's because the only occurrence of an A in the last column is the one that comes before a P. So clearly, the character A, if I'm sitting on this character A, the next character has to be P. Okay, so all I'm doing is using 2 copies of this first column and just illustrating the relationship between one character and what comes after it. There are 2 E characters, so it is a bit of a question which one comes first. But I know that because lexicographical ordering has to be preserved, the first E, well, if the choices are between EA and EP, obviously for the table to be sorted, to be lexicographically sorted, the first row beginning with an E must be followed by an A. The E must be followed by an A. In the second row beginning with an E, the E must be followed by a P. So then I guess the next character is this one, the one in row 6. And so I can illustrate these pairwise relationships without actually writing down the contents of a column of the matrix. Okay, there's the other EP. Similarly with I, L, and N. So I apparently is followed by N. So if I'm at the row beginning with I, the next rotation is the one beginning with N, so I can draw that arrow there. And same thing with the L and the N. And then there's the 3 P rows. So I think, okay, what comes after these 3 Ps? Well, it again comes down to preserving lexicographical order. We know already that the next thing is going to be an I for the first P, so I would draw the arrow from P to the row beginning with I, and then the next one is the L, and the next one is the P. And if you look at this, although I've drawn this as 2 copies of the same column, what I've really done here is produced a permutation of the first column. I've said for each element of the first column, what character comes next. So I can fill that in. And now the question is, okay, so how do I recover the original string from this? My claim is that when you have this mapping, this pairwise mapping of characters, you actually have the ability to recover literally the entire matrix if you want it to. But why would you want to do that? All you want is one row. If I recall correctly, row 6 was the row containing our original string. Let's see if we can recover that. So our original string was 9 characters long. There it is. Let's see if we can recover the original string. Okay, well, if we're in row 6, the first character has to be a P. What comes next? Well, I follow the arrow, and I find myself in row number 3. So I take the next character would be the I. So now I'm in row number 3, and I follow the arrow, and I find myself in row number 5. So the next character is the N, okay? So I'm in row number 5, I follow the arrow, and I get to the E. And you'll see what I'm doing at each step here is just following arrows, and then I walk back to the beginning of the same row and follow the arrow again. Okay, so E goes to A, and then the A goes down to P, and then the P goes to, so the A goes down to this P here. This P, the one at the beginning in row 8, goes to the second P, and then this P here goes to the L, and then the L goes to the E. So I can actually use this mapping. I can just walk through the mapping. I can perform essentially a traversal, just following arrows as I go with this mapping as a way of recovering the original input. And the mapping is a big O-N construction. I just have N characters, and for each character, I have the index of which row it's mapped to. So in this case, for example, I'll just clear everything. In this case, row 7 maps to the next thing. The next row afterwards would be row number 4, the one with the L. And this top to bottom logic, building the mapping the way I did, even works on inputs that don't seem obvious, where I've got a lot of ambiguity. So as before, I remember that there are 4 things that can follow the A. I have the pairs AA, AB, and then 2 other ABs. And so when I build the mapping, I again just leverage the lexicographical order of the table as a way of building it. So I think, okay, well, there are 4 pairs here beginning with A, and they have to be the destination of these 4 A's. So I just make the mapping in the most straightforward possible way in lexicographical order, like that. And there it is. And I do the same thing with all the B's. So the B's can be followed by, which pairs begin with B? I've got BA, 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 BC. Okay, well, I'll just draw the arrows literally in top to bottom order. And you can hopefully already see how I might form a pretty convenient algorithm for this. There actually are even more efficient ones than the obvious one, but the obvious one would just be to say, okay, I've got a big stack of B's, go find all the B's on the right-hand side and just generate the arrows from top to bottom. There are ways to save a little bit of time while doing that, but that's basically the insight. So I've got this one, this one, this one, and this one, and then filling in the C is pretty easy because there's only one C in play. So I've got this, and then I fill in the C. And once I have the mapping, all I have to do is traverse the mapping. So I know because it came with the BWT, I already know what the index of the original string was, so all I have to do is just keep traversing the mapping to generate the right number of characters. I know how many rounds I have to take because it'll be the same number of rounds as there are rows. I just have to walk through the mapping, following arrows between rows until I have every character that I want. So it turns out my original input was this. And you can try that yourself. Try generating the BWT and you will see that you end up with index 6 and the BWT is the string that we started with. And in the earlier example, just for the sake of completeness, in case it wasn't obvious, the original string is the word pineapple. So the actual mapping can be stored essentially as a permutation. That's what this really is saying. An array of indices such that T sub I is the row number of the destination of each arrow. I'd like to try and draw that here, although it's going to be pretty messy. So row 0 is followed by row 8 because that's where the arrow points. It points into row 8. Row 1 is followed by row 0. Row 2 is followed by row 6. So there's row 6. Row 3 is followed by row 5. Row 4 is followed by row 2. Row 5 is followed by row 1. Row 6 is followed by row 3. Row 7 is followed by row 4. Row 8 is followed by row 7. Okay, so hopefully there it is. This is the permutation I would construct. If I use this array T, I can walk along arrows by just indexing into T. So T sub 6, for example, would be 3. And it's just where to go next, where the arrow points. So I just grab the character from the front of each row as I go, and I just walk along using my mapping T. So if I want to actually perform the inversion process, if you give me a BWT and I have to invert the BWT, I would probably do the following. First, I sort the elements of the BWT. So you gave me the data from the last column. I sort them to obtain the first column. I then build that mapping array T, and there are a variety of ways of doing it. There is an algorithm that should be sort of implied by what I just did. There's also one that was described is used in things like bzip and was described, I think, in the paper that originally defined BWT, that is essentially linear time. If you apply various tricks to sort to this first sorting step that would apply. And then once you have the mapping, all you do is walk through the mapping to generate the original string from the permutation. As I mentioned, there is an algorithm to construct the mapping very quickly once you have the elements sorted and with using some sorting related tricks while generating the mapping. When the set of possible symbols is constant, so it's a fixed size set, for example, the set of all 8-bit things, which is what we typically use, we can actually sort things in linear time because we can use bucket sort. I can just create 256 possible buckets and use bucket sort. I can produce the mapping from that sorted representation in linear time as well, also using some tricks like bucket sort. These are algorithm things, so I won't go into much detail. We won't need to implement this ourselves in this offering of the course. It is really interesting, I just don't have hours and hours more to talk about it. So it turns out you can actually invert the BWT in linear time, and the linear time algorithm for inversion is a great deal simpler than the linear time algorithm to compute the forward BWT, which is nice, because if you're writing a decompressor, you'd rather the decompressor be pretty clean, be pretty streamlined. It's okay to take more time in the compressor, but the decompressor should be as fast as possible. So you see the BWT, we didn't talk about zeros and ones, we even talked about some asymptotic stuff. It almost feels like we're talking about, like this is a lecture from an algorithms course. That's great, but we've got to come back to the real world and actually start talking about bit streams again. And so we're going to use this BWT inside of a compression scheme. It will be the BZIP compression scheme in the next lecture. So we're going to go through the entirety of the BZIP scheme, the full BZIP pipeline in the next lecture. In the meantime, maybe we get another break from zeros and ones.